Okay, welcome all to this new reading group session organized by ContinualAI. And today we have the pleasure to host Andrea Cossu from the University of Pisa, who is going to talk about his recent work, Continual Learning for Recurrent Neural Networks, an Empirical Evaluation. And I think that this is one of the first works addressing the topic of continual learning for sequence learning problems, in this case, sequence classification. And I'm very excited to hear from Andrea what would be interesting, I think, insights about applying continual learning strategies, at least what we have developed so far in the context of supervised continual learning and vision, mostly, towards these interesting new tasks and scenarios. So thank you so much, Andrea, for being with us. And please go ahead, the stage is yours.
Great. Thank you, Vincenzo. Thank you very much for the kind introduction. So, as you can see, I'm going to present my recent work on recurrent neural networks, as Vincenzo already said. And note that this is a joint work with Antonio Carta, Vincenzo Lo Monaco himself, and Davide Bacciu. So, basically, we are working on this topic, and we are studying the interplay between recurrent neural networks and continual learning for quite some time now. And so we decided to put together what there is already in this field. And it's not much, but it is something, in our opinion. And also to provide an empirical evaluation, as you can see from the subtitle, let's say. So before starting, since as I already said, we are working on this topic for quite some time. We received also feedbacks from different peoples, including reviewers, of course. So I would like to address the main points usually raised by reviewers or by people with which we talk about this topic. So the first one is this. So the fact that sequential data processing in general is important for continual learning. So sequential data processing is can be addressed with machine learning, usual machine learning techniques, and address problems in which input data comes in the form of sequences. So you have feature vectors connected by time, usually, or anyway, there is a temporal order in the elements of the sequence. And sequential data processing is widespread in many applications in machine learning. Here I am highlighting some applications which are interesting in our opinion for continual learning. So for example, human activity recognition. If you aim to classify what a human is doing, what action is performing, you can simply put sensors on the human and then retrieve the sensor's observations, right? So these observations comes in a sequence because the sensors measure the values in time. Or you may want to predict the activity from the videos. So videos are sequences of frames, so you are back to a sequential problem in which the input is a time series, basically. And note that in this specific case, the sequentiality of the problem is important, because if you have to distinguish between standing up and sitting down, you have to have the temporal order of the frames of the video, because otherwise you can misclassify what was sitting up with sitting down with standing up. So in this case, there is also some crucial aspect in temporal correlation. Other applications are robot control. For example, if you have a robot, it is usually filled with sensors also. And so you receive observation in time again. And there are many things you can do with a robot, but this is also an interesting sequential data processing task. Then we can think about finance. When you have the stock values, you have the sequence of stock values, and you usually want to predict the next value of the stock in, for example, for the next day. And of course, natural language processing is a popular one, since sentences are basically sequences of words. And when you address natural language processing, you are addressing a sequential data processing task in this sense. There are many others, of course. We can go on with this list. But the interesting part of these applications and others is that the environment in which are placed in is highly non-stationary usually. So you can easily introduce or see the drifts occurring in these environments. So they are suitable to continual learning, for continual learning. So for example, the human activity recognition may include what is called a virtual drift, which basically provides you with new classes of activity, which you have to classify. Or robot control, you can perform control on different environments. Finance, of course, if something happens in the world, the time series producing and representing the stock values may suddenly changes. I mean, there are many examples of this. And in natural language processing, you can introduce shift very easily by changing language or changing the domain of the discourse, so that the continual learning is really needed, unless you don't want to, of course, retrain from scratch your model to avoid forgetting. But in this way, you may lose also advantages like forward transfer and so on and so forth. So the gist of this slide is that, in our opinion, sequential data processing is very important and may have very impactful applications for continual learning. The second question, strongly tied to the first one, is that why do you focus on recurrent neural networks? So sequential data processing, okay, we get it. It's important for continual learning, but you can use convolutional neural networks, which are studied in continual learning for vision problems mostly, but anyway, they are studied. Or transformers, which are very effectively, for example, in natural language processing, and all sorts of models. And we agree, this is true. We can use many different models to address sequential data processing tasks, but these are, in our opinion, simply different aspects of the problem. So they generate different questions. We are interested in recurrent neural network as a research problem. So we are also studying recurrent neural networks for sequential data processing. But it would be really interesting to see, and some work is already there, examples of transformers or convolution in sequential data processing for continual learning. Why do we think that recurrent neural networks are worth studying? Basically, they have some properties which may influence the continual learning aspects, like the strategies you apply. So if you consider the number of layers, recurrent neural networks can be thought of a network with a variable number of layers. So when you unroll the network over your input time series, you obtain a feed-forward layer for each element of your time series. So as a result, the length of the depth of the network, the feed-forward unroll the network, depends on the length of the time series. And secondly, the weights are shared over the time steps. So as you may know, as you probably know, the weights of the recurrent neural networks are shared over all the time steps of the sequence. And so this directly influences the backpropagation through time, which is currently the main algorithm used, learning algorithm used to train these deep recurrent networks, like long short-term memory and so on. So since this is a complex interaction, let's say, you may see also different effects on the final result in continual learning when you couple these models with continual learning strategies. And this was our let's say focus. Okay, so to try and understand empirically what does it mean to train these models in continual learning. But first, we took some time and see what was already there in this field. So recurrent neural networks and continual learning are studied currently, but there are very few works in some sense, and very, very few of a general, let's say, on general aspects of recurrent neural networks. Most of them, as we will see, are focused on specific applications, so to say. So the focus is not much on sequential data processing in general, but to solve a specific problem, which is, of course, fine. So by looking at different papers, we organized a shallow taxonomy. So don't think of this as a classification, a very specific application, because, of course, we think that this taxonomy represents well the existing works, but I mean, in the future, it may be superseded by other improvements. But up to now, what we see is that the review, which is a small review, like you can think of about 25 papers, more or less. So a very small and tiny set of papers, which signal that this is a field with potentiality in some sense, right? Because there are not much work on this. But the works that are available basically can be divided in seminal works, which dates back to the late 90s. So it's quite some time that there is this idea of studying recurrent models in continual learning. And they use typically very simple recurrent networks with feedback connections on synthetic benchmarks, in the sense that they are very small benchmarks, so datasets with very few patterns compared to the currently used datasets in machine learning and continual learning. And they are, let's say, disconnected from the reality. So often they are generated like random sequences of binary patterns, something like that. So this, however, highlights that the problem itself was already interesting years ago, before specific applications were thought. So as a research problem, as a pure research problem. And it has been, studied in this sense. Moving on to the more recent works, we can find NLP, so natural language processing, which is kind of driving the literature. There are many, always many compared to the total amount of papers available right now. But there are many papers on natural language processing, which solves often specific applications. So you have a natural language processing task, there is some drift in this task, and so you apply continual learning. So this is more or less the sense of most of the works, which are very interesting in my opinion, but are application specific by their nature. Another family, like with few works, let's say, is the family we call bio-inspired and alternative in general recurrent paradigms. So basically, here you can find an example of spiking networks, for example, or alternative to backpropagation through time as a learning algorithm, custom architectures, not spiking, but custom in the sense that they are maybe modular and use specific modules. So in this way, the authors try to study the problem directly by searching for solution to solve the problem without using the existing, let's say, the existing models and strategies. So this is a very custom ad hoc approach, which may work well, of course, because they are specifically designed to solve the continual learning problem, but currently they are not scaling much yet, of course. So I think that these are a very promising path, but up to now, there is still a lot of work to do before being able to tackle more realistic benchmarks. And finally, there is the deep networks, deep recurrent networks like long short-term memory and GRU. So these are the more general the more general studies, which, for example, apply architectural approaches to a recurrent model in order to be able to mitigate forgetting, and so on and so forth. So this work, our work, in some sense, belongs to this category because we studied long short-term memory network as a representative for the recurrent neural networks, for the deep recurrent neural networks. And in general, if you see across all these categories, you can see that the vast majority of works focus on new models or on new continual learning strategies. And you can see this by also looking at the paper. Of course, here we don't have the space in the slide and the time to cover this. But if you read the paper, you will easily see that this is the case. And again, this is good, in my opinion. Many solutions, many different ideas are needed before converging maybe to some more promising ones. So this is good, but I also believe that it is important to understand the behavior of what is already there before, or while at the same time exploring new ideas. And the fact that most of the, let's say, works introduce a novel approach, or anyway, the fact that this field is quite new, in my opinion, reflects in this table. So in the paper, we also reviewed, let's say, the benchmarks used in those papers, in the papers organized here. And you can see that compared to the number of papers I said before, there are many benchmarks. So this means that there is no standard in this field yet. There is no benchmark used by many papers. As you can see by looking at the citations, the references next to the dataset and benchmark name. Okay, there are very few, one paper, two papers at most. And this is quite interesting, in my opinion, and also highlight the need for something, I mean, more general, that can be used from different papers and from different purposes. Like in computer vision, I mean, we have tons of papers, and compared to that amount, few benchmarks, right, for computer vision. So after this review, I want to highlight again our objective more clearly, which is the study of the behavior of recurrent neural networks, the deep recurrent networks we are accustomed to from the machine learning field, so long short-term memory, GRU, these kind of architectures. And we studied this behavior by applying popular continual learning strategies which are not designed specifically for sequential data processing. So we tried to draw some general, as general as possible, conclusions from our experiments. So we didn't want to tie ourselves to a specific solution. And the other point is that the benchmarks should be application agnostic as much as possible. Of course, it does not exist a benchmark which is application agnostic, because if it is a benchmark, it is a data set taken from somewhere. So there is an application behind it, unless it is a random one, but this is not the case. We will see which benchmarks we used. And currently, in this paper, we focused on sequence classification. So in this picture, you see a sequence, more or less, kind of. So these are the elements of the sequence. Each element is a feature vector. And the sequence J, in this case, has T time steps. And at the end of the sequence, you receive a label and you produce an output. And so you have to classify the entire sequence after seeing all the sequence. And there are benchmarks which are designed for this purpose. Before showing you the benchmarks, just a quick word about the experimental settings we use. So we are in a class-incremental mostly, we will see, class-incremental scenario. So we are receiving new classes as new experiences, new steps, new tasks. You call it as you want. We call it experiences, but as new data comes in, we receive new classes. So we have to train our models on new classes without forgetting the previous ones, the usual scenario in continual learning. We don't use task labels, neither at training time nor at test time. And therefore, we use a single head model in which the output layer is not partitioned in any way. Even if in the paper you will find a brief comparison also with multi-head approaches, so with task label used at test time, just to see the difference in performances also with recurrent models. We will not cover this, but it is quite intuitive, the result. Our strategies, the strategies we compare our models with, are 6 basically. So they are taken from regularization strategies, different kinds of regularization strategies, from replay and from hybrid approaches. So EWC and memory-aware synapses mass are importance-based regularization strategies. Basically, they don't work in class incremental. We more or less already know this. Also for recurrent neural networks, even if it has not been proved, but it is quite straightforward because the output layer is not recurrent in some sense. So it's intuitive to know that these won't work in this setting, but we need them because we are not working only on this setting, as we will see in a moment. And then learning without forgetting is a regularization strategies based on distillation. I'm not going into the details of these strategies. They are quite popular. This was the objective. But anyway, if you have questions, you can ask. And the gradient and average gradient episodic memory are hybrid in the sense that they store previous patterns like replay strategies, but then they don't do full replay, but they project the gradient in orthogonal directions to prevent forgetting. And finally, the replay, the most simple one, I think, so random sampling from the training data set into the memory, to the replay memory, so that we are not choosing a specific replay policy so that our results then are dependent on the specific replay policy. We want to be as general as possible, as previously mentioned. We decided to not use architectural strategies. We worked already on a specific architectural strategies for recurrent neural networks in a previous paper. And moreover, there is a variety of architectural strategies outside sequential data processing, so for computer vision and continual learning, for example. And it is very difficult to choose a representative for this strategy, for this family of strategy. So we prefer to avoid entering in this complex field. We think that this is a very promising approach because architectural strategies may be very effective, especially against forgetting, even if they have other problems. But we thought of this as a different question. And just to give you a sense of how experiments were performed, we performed a grid search. So there is a model selection phase and a model assessment phase in which we establish the performance of the best model. The model selection is performed on a held out number of experiences. So if you think about permuted MNIST, we took like 3 permutations to do model selections, and we evaluate the best model on other different 10 permutations. Okay. For the experiments, you will find the link to the GitHub repository in the paper, and this paper was the experiments of this paper were performed in the middle of the Avalanche, the continual learning library developed by ContinualAI, in the middle of the Avalanche development. So it has been quite a mess in this sense. So at some point we switched also to Avalanche. Of course, the repository doesn't use Avalanche because the beginning of the experiments, in the beginning, Avalanche was not available. And we plan to move these all to Avalanche. But anyway, the experiments are for now reproducible without Avalanche. Okay. Okay, so the benchmarks, before looking at the results, are 2 taken directly, basically, from the computer vision world, the split and permuted MNIST. I know that you may don't like these benchmarks very much, but they're useful for us because we are interested in studying a specific property of the recurrent networks connected to the peculiarities we discussed before, which is the sequence length. And with these benchmarks, which are application agnostic in some sense because they are very simple, also recognized by the continual learning community as very simple. And we can transform very easily these images, these benchmarks of images into sequences by taking a subset of pixels at a time. So from an image, if you take 4 pixels at a time, you obtain a sequence in which each element is a vector of 4 features, of dimension 4, and you concatenate all the 4 pixels in a sequence until you reach the end of the image. And so we can, let's say, use this benchmark with recurrent neural networks. But then to also test the performance on more, let's say, on benchmarks in which the data are taken from sequential applications, we identified 2 existing datasets like synthetic speech commands and quick draw. So the first one is an audio dataset. Each audio sample is a word, a spoken word. So you have to classify the word of that audio sample. And they have fixed length, 101 time steps, preprocessed in this way, as you can see from this picture. So each row is a feature vector, and it has 40 elements. It's an audio preprocessing with MEL features. It's quite a standard preprocessing. So it doesn't need any particular models, and this is why we choose this benchmark. And it is also the most simple one among the 2. The other one is quick draw, which basically is a drawing, is a large data set of drawings. And the sequence is the sequence of pen strokes. So you have the coordinates of the pen, and you have to classify the final image at the end of the entire sequence of pen strokes. And this is variable in sequence length, of course, because when you draw something, you don't have to. You are not forced to use always the same amount of strokes to draw something. And so the sequence length varies between like 20 steps and 120 steps, more or less. Okay, finally, we are able to see some results. And this is, I think, the main result of our evaluation. And the title says that sequence length affects forgetting, and this is let's say the experimental assessment of this statement. On the y-axis, you see the accuracy, the average accuracy computed at the end of the training on all the data, on all the experiences, and it is computed on the entire set of data. So on the x-axis, you have basically the sequence length. The first here is also, you find also the model name, because the model, of course, influences the sequence length. We compared also with multi-layer perceptron, in which the sequence length is 1, because we take all the pixels together. Here, you are looking at permuted MNIST on the left and on split MNIST on the right. Then we start taking images, subset of pixels at a time. So raw LSTM is a long short-term memory which takes 28 pixels at a time, so a row of the image at a time, resulting in 28 sequences, in 28 steps for each sequence. Then LSTM 16, so 16 pixels at a time, resulting in a sequence with 49 steps, and so on and so forth. So as you go to the right, the sequence length increases and the performance decreases quite rapidly. This is the domain incremental. So this on the left is not class incremental because it is permuted MNIST. So you are seeing new instances basically of previously existing classes. And this is like the most simple benchmark I can think of for continual learning. So permuted MNIST is something which is, I think, at the best of my knowledge, as we say, it's one of the simplest benchmarks in continual learning. And so, in fact, you can see that the multi-layer perceptron here performs quite well. But as soon as you are treating things like sequences, the performance decreases. And replay is quite good in this sense to maintain performances, but all the strategies show this trend, right? So all the strategies show a decreasing performance as the sequence length increases. And like EWC, for example, is one of the strategy which we know works very well in permuted MNIST scenario. So it's basically like replay and gradient episodic memory in performance when applied to multi-layer perceptron. When you apply to sequential data processing, the performance drops very, very quickly, resulting in this final, let's say, 30%. And so this is a very interesting fact, because even on very simple benchmarks like this, the performance is reducing very quickly. On the right, you can see the same, basically. So we drop the importance-based regularization approaches like EWC and memory-aware synapses, which we know they don't work in this setting. So on the graph, you can see these, the remaining strategies. And you can see that the gradient episodic memory type of approach is working very well, even better than replay, even if the standard deviations overlap. Anyway, it's performing very well. But the performance is still decreasing at when the sequence length increases. And the learning without forgetting is quite surprising, because learning without forgetting, again, works well on split MNIST, on multi-layer perceptron, but then basically it goes to the random performance, approaches the random performances as you increase the length of the sequence. So these are very different kind of approaches, but they are showing similar results with different, let's say, impacts. So replay is more robust. Of course, these are the size basically of the mini batches replayed. So if you replay 1 pattern per mini batch or 10 patterns per mini batch and so on and so forth. So as more replay patterns are added, of course, the performance improves, but improves slower basically. So you need more patterns as the sequence length improves. So even on replay increases. So even on replay strategies, there is this effect on our benchmarks. Okay, but these are the results. I'm showing you the table because here the sequence length is more or less fixed in some sense, so given by the data set. On SSC, so the audio benchmark of speech classification, and quick draw, the drawing classification from sketches. The naive and joint training are the lower bound, let's say, and the upper bound. So naive is the fine-tuning, simply, without any continual learning approaches, and the joint training is the training on the entire dataset. And also, as you can see, okay, we know that EWC and these strategies won't work, but the gradient episodic memory, which was quite strong here, okay, similar in performance, comparable in performance to replay, drops the performance. So in this case, with respect to replay, so replay performs quite well, even if there is still this this difference when considering a sequence or the entire pattern at once. So in this case, the multi-layer perceptron is trained by taking all the elements of the sequence at once. So it doesn't count the temporal order. They are all different features for the multi-layer perceptron. And the replay is performing quite well in this scenario, of course. The multi-layer perceptron also is quite effective because the data set here is quite general. I mean, it's not here, the synthetic speech commands. It's not a very challenging audio data set. But the thing is that the gradient episodic memory is now having some difficulties. So as soon as we move from very simple benchmarks in terms of the patterns which are in the benchmark, so the images of MNIST, as soon as we move to more complex patterns, the gradient episodic memory is is able to mitigate forgetting in the sense that the training accuracy decreases, so the overall performance in accuracy is lower, But the problem here is not forgetting, it's more the training accuracy. So these are benchmarks with 10 experiences. So you see in total 20 classes, 2 classes at a time in both benchmarks. So on long sequences of experiences, you see that maybe because the projection, I mean, it's a very impactful trade-off required by the strategy. You have to change the learning trajectory. You have an optimal one for the current data, but you change it because you project the gradient in order to mitigate forgetting. So you move away, in some sense, from the optimal trajectory found by Adam or stochastic gradient descent. And this impact in the training performance. So this is a different problem, but still an interesting one, because if you solve the training problem here, GEM is quite good in mitigating forgetting, so you may reach the performance of replay. And finally, for quick draw, we don't use multilayer perceptron because the sequences have variable sequence length. So, I mean, it doesn't make much sense to use multilayer perceptron. You can pad, but it is a very long padding because we go from 20 to 120 sequence length. So, I mean, it's not something ideal for a multilayer perceptron. And also here you can see that more or less there is the same trend. So gradient episodic memory, again, loses in training, and here replay has a lower performance because the dataset is a bit more complex than SSC. So we may need more patterns. Of course, if you train with replay and increase the patterns, you will always you will always approach the joint training performance because that's the way it is trained, basically, more or less. But here, if the number of patterns is the same with respect to SSC, the performance, the absolute performance is lower. So as we can see, I mean, there is a general trend of different continual learning strategies. It is not like we can blindly apply any continual learning strategy to sequential data processing and hope for the best, because it may work sometime, but it is not always the case. So we are just scratching the surface literally because there are very few works on this. Basically, none of them review made an empirical evaluation in class incremental settings, so the ones which are studied nowadays. The multitask with multi-ed approach is now, in some sense, losing interest, at least by seeing the papers published currently in continual learning. And so this is the first paper doing this, we think. Well, we are almost sure. We looked a lot for references in this topic. And so we think that this can be useful, one, to understand the problem, so to make evident that you have to pay attention. You have maybe to do some experiments first before jumping to conclusions, okay, when applying to recurrent networks. And to also sketch, of course, some future directions, but there are many future directions in this case because there are few existing directions. So in general, you can adapt the existing continual learning strategies. Okay, so GEM seem a good approach also for recurrent models. The forgetting is quite mitigated in this case. We just need to improve the trade-off with the training performance. So maybe this time is best to focus on the training performance instead of the forgetting, and of course without losing in that aspect too. Another interesting avenue, in my opinion, is similar to bio-inspired and alternative recurrent paradigms we saw before. So looking for alternatives to backpropagation through time, because this algorithm is largely influenced by sharing weights through time steps, unrolling of the network, the properties we saw at the beginning. So it may be good if you want to tackle very well a specific task, but in continual learning, it has some disadvantages. For example, in EWC, on permuted MNIST, the performance may be decreasing because the importance values associated to each weight, if you know how EWC work, are either exploding or vanishing. and I'm using these terms because in recurrent networks, due to the unrolling and backpropagation through time with the shear weights, you may have the exploding and vanishing gradient. So the exploding gradient you can clip and solve the problem. The vanishing gradient, basically there is no solution up to now, no general solution. So if the gradient associated to the recurrent weight is very, very low, you will obtain very, very low importance values for all the recurrent importances, okay? And so you are saying that the recurrent part of the network is free to change because you don't care, because they are not important weights. And so, I mean, this is not good for continual learning. So this is a problem, one of the problems. So maybe local algorithms can help in this, but I don't have the solution, unfortunately. Otherwise, this would have been, well, there would have been another slide with the solution. And also, I think that in parallel, of course, new solution and so on and so forth, new approaches, but we have also to do something, to do some tests outside these, which are good, but are not enough alone. So just place something somewhere in the sense. Sequential data processing is widespread, so we can easily find an application. Just put, for example, I have in mind from quite some time the weather prediction. You put something in outside which try to predict the weather given the sensor observations, and you try different strategies in the wild, so to say. So also seeing more applications to raise the interest in the problem, attract people to work on the problem could be, I mean, not a very specific to research alone, but also to improving the perspective we have on the problem right now. So if you now believe or are interested or convinced that recurrent neural networks are worth studying, I'm happy. Otherwise, I mean, you can look at the paper and hope that this will make you change your mind. You can contact me, you can ask questions, and thank you very much for the attention.
Thank you, Andrea, so much for your very interesting and calm, I would say, very relaxing talk.
I hope you didn't fall asleep.
No. Actually, I enjoyed the, let's say, relaxed pace, because you can really listen to what you're saying, right? So that's great. Yes. One question, maybe to break the ice before letting also the audience ask their questions through the chat or just opening their mic. So how do you see, I mean, the future of, let's say, the application of continual learning to sequence learning problems? I mean, you have explained that it is indeed interesting to think at continual learning also. And maybe all the continual learning problem also in terms of the ability to learn sequences and to process sequences. And I guess that all of us agree that that's important. But do you have like maybe more specific insights about the future of these? I mean, you have focused now on sequence classification, right? So what do you think are scenarios, tasks that would be like the next stage of the research in this area?
Yeah, you're right. We are focusing on sequence classification. The choice is, I mean, due to the fact that the works on continual learning, also outside sequential data processing, are centered on this problem of classification, which translates in sequence classification for sequential data processing. Because in sequential data processing, when you deal with sequences, you have different kind of tasks. So you have sequence classification, in which you have the entire sequence, which corresponds to a pattern of computer vision, an image, and you have to classify that pattern. So sequence classification corresponds to the classification on computer vision, for example. But you also have different kind of tasks, like sequence to sequence. For translation, for example, you transform a sequence, an input sequence, into another one, which is the target. Or you have element to element, so each element of the sequence is associated to a prediction. For example, weather prediction I was mentioning before, it is one example. Here you have the sensor observation at a specific time, for example, for a day, and you predict the weather class, which is sunny, and I don't know, cloudy and so on for that day. So on each day you have to predict something. It's not sequence classification. It's something more complex in some way. And so this is amenable to different scenarios. So we can extend this outside the standard continual learning scenario, in which you have your patterns and you classify or do something with them, but move towards something in which there is the real world. So you receive a stream of data, sensor observation of something, and you predict at each time step what is happening. So the sequence modeling problem is a very general problem, which help also in downstream tasks, as seen in natural language processing. So the combination between these two scenarios may, in my opinion, bring new, let's say, innovation in continual learning. You have the opportunity to model what is coming next with sequence modeling, predict the next step, which is another task, which is an unsupervised task. You don't need the label. You can always do this task. Just place something somewhere and do sequence modeling. You can do that. And there are drifts, of course. So unsupervised learning is also prone to forgetting. Maybe not as much as class-incremental scenarios, but there is forgetting also. And then you can do whatever you want, basically. You can predict the next step. You can predict a class from the current time. You can wait for a moment and then predict something. So in the audio, you often have to predict the class, or a value, a prediction every now and then. So maybe in this time I predict something, then no prediction, then another one, because you, for example, predict the boundaries of the words, character by character. So I think that this interplay is interesting. Studying this, which has yet received less attention, but it has more potential for also practical applications, because sequence classification has applications, but in my opinion is more limited with respect to the realm of different tasks we can do in sequential data processing.
Yeah, but
I don't know if that answers your question.
Yeah, that's great. I totally agree with you, and so I will be happy to see follow-up works on this topic. So do we have a question for Andrea from the people attending? Yes, so we have a question in the chat. Transformer models are very popular in recent days for sequential data, right? I think that you also quickly went through that. Is it a right direction to pursue continual learning in recurrent neural networks?
Yeah, this is of course an interesting question. So it is something we discussed also, well, not today much, but it is an important question, because there is this thing that now that transformers are very effective for many different tasks, I mean, what is the sense in using recurrent neural networks? So it is an old model, like the old guy, which goes low because they are slower, of course.
They are old.
Then they are old, slow. So, but I think that there are two separate points of view. So one is that, biologically speaking, and this I know could break the audience into groups, the ones that like bio-inspired approaches and the ones that don't. But I mean, if we look at bio-inspired approaches, some form of recurrent connections are needed. So the feedback, the reverberating activation is a concept which is more or less widespread. So this is a short point. The other point is that for some tasks, it is still, in my opinion, practical task, it is still important to use recurrent networks, because transformer are good, okay, but for example, with variable sequence length, you have to pad, you have to go all the way down with the sliding window approach. So you take a window and you made it slide on the sequence and so on and so forth, much like you can do with one DCNN. And this is costly. So in some cases, it may be like shooting with a cannon to hit a mosquito. So not much advantages. But of course, in natural language processing, for example, okay, if you have to do a language modeling on Wikipedia and then do downstream tasks, I wouldn't use a recurrent networks nowadays for practical applications. You can do it for research, of course. But so, I mean, it really depends on your objective. For continual learning, I think it is still important because we are not interested much in scaling to gigantic data sets, because this is the machine learning approach. You have a single data set and you scale on that, but we have to learn incrementally. So usually we receive less data, a few data at a time. So we don't have like the need to have a gigantic model behind if you are able to exploit the weights and the knowledge we have already inside the model. So I think that for continual learning, it's still worth studying the recurrent model.
Okay, anything else? Antonio, I saw you.
Yeah,
mic.
I wanted to add something. I think that in general, the literature on transformers is moving slowly, but towards more scalable models. And like there are many kinds of scalable approaches for transformers, but one of the idea could be like combining recurrence and attention. In the end, this is like the ideal approach if you want to have a unbounded context, let's say. So I think there is a need for a transformer-like model able to use attention, but in a scalable way. And this scalability it needs to come from the model side, so the architecture of the model, but at some point it will also need to be at the training level side, so like continual learning. Maybe we are not there yet, but we will arrive there at some point. Okay, and that's all.
Yeah, thanks, Antonio, for the comment. And yes, I do also believe that we need to study all these models for sequence modeling and continual learning, so that we can get better insights about what's working, what's not, and maybe possibly combine them together and their features in a new original way. So thank you all for joining for this reading group session. We will meet again for the next session next week, same time, for let me see if I can get this right, with a new paper from the JUST group in Barcelona that is called ICAE Remind for online continual learning with compressed feature replay. So stay tuned for the next week, and thank you so much, Andrea, again. Send us your slides if you want, so that we can upload them on the forum with a topic that is already there for you and for the other people here to continue this interesting discussion. So thank you so much, and see you next week. Bye.
Bye-bye.
Bye.